Okay, algorithms. So what is an algorithm? So what you are seeing here, if the picture is small, you can just make your window full screen. That way you can see it bigger. Uh, yeah, there's no way I can make it bigger unless if I do this. That's I want the whole space to write something. So uh, algorithm, for example, let me give you an example. Let's say you have to go from let's think about some road, road. So let's say these are different roads. Road A, B, C, D, and then maybe 1, 2, 3. So let's say you have to go from point A, point X to point. So if you just think about a GPS, it will give you direction. So that's an example of an algorithm. It will say start. So you start here, start, and it will say go in this direction. So we will call it east, and maybe that is north. Go east until point B, and then turn left until point. So this is we will refer this as point 3B. This will be 2B, and then until 2B, and then go east again until you reach your destination. So that's an algorithm. So you will just write here, go. The first step for algorithm will be go east. I'm just writing briefly. North. You have to, specify exactly, and then east again. You have to say the endpoint to start. So the input will be, in that case, for this algorithm, the input might be saying, okay, I want to go to Y. So that's the destination. So for this particular algorithm, for this GPS guide, there's no output, but I will come to another example where there will be an output too. So let's go to that algorithm. So here is another example. So this might be familiar to you from last time. Uh, so this is the computing the velocity of a falling object. So that is the algorithm here, and you might recognize this, that equation. V ti plus 1, the velocity at time t plus 1 is Vti is the velocity at time ti. The difference between times that g minus c over m, Vti, where c is a constant, a drag constant, m is the mass, g is the gravitational acceleration. Right. So probably my previous example was a little bit sketchy, whereas here we have all the elements of an algorithm that I defined in that block diagram. All of them are valid. I mean, I say that there's no single way to define an algorithm. At the same time, sometimes you can have many different ways to write an algorithm. In this lecture, we will see as many examples as we can, and hope you do your own research and get comfortable with this concept. That's the important thing. So here, what is the input? Yeah, and also if you look at this, we went through this example a little bit, so I can say that this is like one iteration. This is one iteration is shown above. That is, if you are given time, present time, and ti plus 1 is at what time you want the velocity, ti plus 1, and the vt, what is the velocity at present time ti, then you can use this formula. So it's just one application of formula, and then you have your output. That's a very simple algorithm. Just one line algorithm. So you have just, if you have these three inputs, and you can compute output. So let me write a table here: T1, T2, T3, T4, T5. No, let's say I have 5 times. So let's say this is time 0, 2 seconds, 2 seconds, 5 seconds, 10 seconds, and 20 seconds. So we want to find the velocity at these time instances. So from here to here, I will apply the algorithm shown. So this algorithm will be applied there to find the velocity there. So here, we already know the initial velocity should be known. So Vti is known, Vt1 is known. So from applying algorithm, Vt2 can be computed. Now, if I write this a little bit clearly. So in this case, how the algorithm, so I'm going to name this algorithm because algorithm is a general term. So let me name this algorithm. If you look at the lecture note, I gave a name called VL. So let's put a name to this algorithm. The name of the algorithm is VLUPDT, well update, velocity update, short form. So let me write how I will apply this algorithm. So VT2 is well upped. So that algorithm has 3 input: T1, T2, and VT1. VT2 is velocity. Give the algorithm T1, T2, VT1. I can do the same to find T3. So VT3, I will apply the algorithm one more time. Velocity update. Now, T1 is the present time. So the present time now is T2. T2. The next time we want it at T3. And the velocity at time T2 is VT2. We just got it in the previous step. Is that clear? This is probably a new concept for all of you. So make sure you understand. There are many questions. I put a homework question around this, so you need to be comfortable with this. So similarly, for example, can somebody answer this? Let me copy this. Okay. So let's say, let's erase this all of this. Can I go about and write this? Let's say I want to find VT4. So how can I write it? So if I write this for the first time, is it correct? VT4 is, if I just follow the algorithm, well upped velocity update, the present time. So what is the present time? So I didn't write all those previous steps. So we have a question: where should we start? And the initial, you can always assume. We'll assume the initial is known. Initial state is known. So, okay, somebody is saying I should start at T3. So let me write that way, and we will see if there's a problem. So we will write T3, and then we want it at T4, VT3. That is correct. Yes, well update means velocity update. Is this correct? Or what is the problem with that? The problem is we don't know what is VT3. we don't know what is VT3. We don't know. We know the initial state, which is at time t0, or what we call t1, time is equal to zero, the velocity we usually assume as 0. So initial, so somebody saying we should start at the initial state. So yes, that's so let me change that. So somebody saying we should start at the initial state. So I will say t1, and then I want it at t4. So this should be t1. So I mean, okay, yeah. There are a lot of questions. As I said, this is a new concept. So what I'm trying to get at is, even though we have these time steps, there are two ways to compute the velocity at time 4. Okay, one, I have to just compute the velocity at time 2, and from there I compute the velocity at time 3, and then from there I compute the velocity at time 4. We have to do it sequentially. But if you want to do it directly, there's one way to do it. I can just compute this directly. So that is what you are seeing on the board now is that solution. So here T2 minus T4 minus T1 is a big time. T4 minus T1 is 10 seconds. So it is taking a big step, but you can compute. But so now, what are the differences? Can someone get, so I hope you understand these two different ways of writing this velocity at T4. One is take one step, go from 0 to 4. It's a big time window, big time step, and you can compute that. Or you do it sequentially. What is the advantage of this? So so we have two scenarios here. One is T1, T2, T3, T4, and T5. This is where we want to compute the velocity, let's say. So one approach is going step by step from T1 to T2, compute the velocity at VT2, use that to compute the velocity at VT3, use that to compute the velocity at VT4. So let me call it approach 1. That will work. Another approach is you just compute from here. So that is also, it will give you VT4. Now for the second approach, you will write VT4 is well, update T1, T4, and VT1. That is for the second approach, so approach 2. So that is approach 2. For approach 1, you will write VT2 is, well, update T1, T2, VT1, and then you will write VT3 is, well, update T2, T3, VT2, and then VT4 is, well, update T3, T4, VT3. Let's compare these two approaches. So that is approach 2. Approach 1, sorry. What can we say about complexity, computational complexity? Now, approach one, you just you had to do, you had to do three steps. So now, well, rather than complexity, let me call it rather than computational complexity. Oops, let me call it coding complexity. Approach one is high, less. Now accuracy, because this is a estimate of the true velocity. We already have an analog, analytic formula for the true velocity. What can you say about true velocity? Accuracy. Which one is better? Which one will give you the better accuracy? Approach one or approach two? Approach one. So high accuracy, it is better than low accuracy. So why? So I mean, it begs the question, why? To see why, I need which lecture has an analysis. So let me see. Lectures, error analysis. The answer is in lecture 3. So why? The answer probably also in Fourier series. I mean Taylor series. So maybe lecture 3 and 4. Because this is an iterative app, you compute the velocity. Your current accuracy depends on the previous estimation. So if you make a big step, we will see that it will prone to high, errors. So somebody was asking a question. Go ahead and you can talk. Any questions? No questions? Okay. So well, it is now the approximation, the accuracy of the approximation depends on the step size. So if you have smaller steps, so this is a step size. If you have a smaller step size times f, the accuracy will be better. Since you are taking a big step, there's an error corresponding to that. So that's the answer to that. What exactly is velocity update? That's coming. This problem, this velocity update problem, is coming from lecture 1. So is that answer the question? Because if you look at this algorithm, which all the physics behind it was explained in lecture 1. So you compute the next velocity based on present velocity. That's the numerical solution to this partial differential equation problem, which was introduced in lecture 1. Okay. So now I'm going to probably, if you thought that was a little bit tough example, I'm going to go because my goal in this lecture is to explain algorithm. So let's look at a very simple example. So let's think about now a computer program. I'm sure many of you are familiar with what a computer program is now. So let's think about a computer program. Think about the computer program. that outputs numbers from 1 to 10. That outputs, on the screen it will display some numbers. Okay, so I forgot to introduce one thing. Anyway, it will come. It is called pseudocode. So I'm going to write a pseudocode for this algorithm. Even though there was a pseudocode for this one too, I didn't introduce it as a pseudocode. Where is that? Okay, I didn't write it, but let's go to this one. The pseudocode for this algorithm is so we have to display. I mean, it is very too simple, probably. We have to just say for I is 1 to 10. It is like a counter. We can just display I. And so this is not a program. This is not a program. And if you just run this in C++, it is not going to run. So this is a pseudocode. So what is a pseudocode? Something that is better than a paragraph. That is a structured way of explaining an algorithm. A structured approach. Of explaining the goal of an algorithm. The goal for us was to display numbers from 1 to 10. So, but let me distinguish with the actual program. So if you have to do this, implement this above pseudocode, in an actual program, you have to follow certain structures. For example, let me write something and we will. Somebody was asking, can a main block diagram be a pseudocode? Yeah, but I mean, the only reason why, if you are, let's say you are restricted to a text pad where there's no way you can draw a block, there's no way you can draw a line, then you have to only use text. So most of the time, a pseudocode is written using like a step text, but a block, if you have the freedom, it probably is, if it is better than the. Well, okay, let me answer that in this course. For example, if I ask you to write a pseudocode, can you write a block diagram? No, you have to write it. If I ask you to write it, because that's why it is called block diagram. Yes, they are similar. The concept is similar. It is called different thing. It is called a block diagram. So I will ask, okay, write this algorithm as a block diagram. Or I will write this algorithm as pseudocode, because these are clearly two different things, but they serve the same purpose. Don't mistake that. These are very similar in terms of their purpose. I'm going to write a very simple C++ program, then we will discuss it. We will discuss every step of it. See, the same, that thing that I probably you will do this in your introduction to C++. Now, these two are identical in terms of what they do. These two are identical. The first one, the pseudocode, there is no, there is no strict rule, as long as we understand, we all understand. If we just read the pseudocode, we all understand. We had basically from 1 to 10, we had to display the number I count. Whereas on the second one, if we have to implement that in C++, you have to follow a certain syntax. Even if you make one mistake, if you just miss a bracket, it is not going to compile, because this program should be interpreted by a machine language and machine interpreter, and it need to compile it, and it had to actually run. So because there cannot be ambiguity of what you do, because end of the day, computer has to implement it. Whereas in pseudocode, that's the difference between pseudocode and an actual program. In pseudocode, there is an ambiguity. Yes, we left it as ambiguous because it is not so important. Maybe it is so trivial, or maybe there are different ways to do it, and so we leave it as an ambiguity. Whereas if you implement this in an actual program, you have to know how to implement it. So what you should do, so what is the role of pseudocode in programming? The pseudocode is useful to organize our thoughts, because before we program something, we need to decide, especially when it comes to complex programs. We want to, we're going to put a picture of that program, how it is going to run, where things might go wrong, all of that. We want to do it rather than just thinking about it, writing this block diagram or pseudocode helps. So it is like a planning. It's a planning. When you have to plan something, you always get a paper and pencil and you sketch something, or you put some steps, and that is what it is. Pseudocode is a list of things to do in programs. So it tells the important things, but when you go to C++ or any other program, you will have to execute every syntax that is required by whoever designed that program. And C++ is a program that somebody developed to interpret the code that you write into machine execution. Okay, so I hope that gives some introduction about what a pseudocode is. My goal is to introduce pseudocode, not C++, because you are going to write these codes in the lab. You're already getting familiar with all this syntax of C++, so you will use all of that. And then when I give a pseudocode, you will implement that hopefully in any program. In this class, it's in C++. So let me go to a slightly complex algorithm. So it is the sorting algorithm. First of all, let me explain what a sorting algorithm is. So let's say this is a sorting algorithm. Sorting algorithm. So it has an input, as I introduced before, it has an input. So let's say in this case, input is a list of numbers. I'm going to write this as an array. 6, 5, 9, 7, 8, 3, 4. Output of this algorithm is going to be 3, 4, 5, 6, 7, 8, 9. So what happened? Obviously, there are two ways to store. One is ascending, other one is descending. We are assuming it is ascending. Again, that is left. Now, so this algorithm took a series of numbers and it sorted it. It sorted them, for simply, we will just assume ascending. So the algorithm input was a series of 7 numbers. 7 numbers was given to the algorithm, and then it sorted it and gives an output. So how should the algorithm work? So what is, how would you sort it? If I look at it, I see all these numbers. I know there is 3, 4, 8, 7. I can just sort it. If I have by mind, I just look at it and I can just easily sort this. I can just write, it makes sense. The output makes sense for all of us that yes, it is. Yes, go ahead and ask. There's a question.
No, I'm just trying to suggest how you do it. Would you first have to list all the integers first in the program before, and then start, then write the algorithm?
Well, you should, let's think like an algorithm. Now, if you're an algorithm, the algorithm doesn't know. Well, if you yes, you have to assume it is integers. Forget about the other numbers. We only talk about integers, and the algorithm should know. Since it is input is already given, it will know, okay, what is the size of this array? Here, the size of the array is 7. Then the algorithm had to decide how I'm going to organize them from smaller to largest. Did I answer your question? Okay. So what I want, there is a big difference between what an algorithm can do and what we can do. We are so good at sorting this, 7-digit number. But if you are given a number, if I just increase this digit to, I don't know, 70, we will take at least 5 minutes to sort that. Whereas an algorithm can do that in a fraction of a second. So yes, this is only an example, but the sorting algorithm is useful, because you are given 1,000 numbers, probably you won't finish it in one day because it takes so long. But if you use a certain structure, probably even we can do it. If you use a certain strategy, probably even we can do it faster. So let's think about an algorithm, how it is going to sort this. So in the lecture note, I have written an algorithm to sort this. So I'm going to explain that algorithm. So I'm going to name this A. So A, so it's A is that vector 6, 5, 9, 7, 8, 3, 4. That is A. Now let's also A1, A1, A2, A3, A4, A5, A6, and A7. So A1 is 6, A2 is 5, A3 is 9, 7, 8, 3, 4. Now we are going to, let me restate the goal here. We are going to change the goal. If we are going to organize the numbers in A in a way that it is going to be this. 3, 4, 5, 6, 7, 8, 9. So A1 is 3, A2 is 4, A7 is 9. So once again, that is A. So we went, you can just think of this A as, as a box containing, 7 pouches. And then we will address the first pouch as A1, second as A2, third as A3, and so on. So obviously we want to have the smallest number in the first pouch, next smallest number in the second pouch, and the largest number in the seventh pouch. So that is what is called sorting. So now we made a little bit of rules. So the first element of A now has 6. We want the smallest number. You want to place the smallest number there. So now I define an important concept here, that the number is an array. So array is a series of locations. Each can hold an integer. Later we'll study that in computers numbers are stored by binary. So probably that's a difference. So here we'll just pretend computers can contain integer numbers. Okay, and we can program that. You can declare an array in C++. That is an integer. So it's totally possible because C++ is a little bit higher level language, whereas there are different levels of language. There are lower level language that only deal with binary numbers, zeros and one, whereas C++ is a slightly higher language. So there's an interpreter between C++ and this lower level language that will interpret whatever we are saying here. So if we say A is an array of integers, that will interpret to the lower level program. Yeah, they mean that integer means there is no fractions and things like that. We'll get a little bit into that I think in the next lecture, of how it is done, how these programs are represented and so on. Okay, so let's, since we done declaring what is an array, what is the contents of an array. So each pouch in this array contains one integer. So on the top we have the present array, and the second I'm showing what we want, what is the output that we want. So I think now we are ready to write this pseudocode. It's not even a program. So it isn't, I should have copy pasted here. I don't think I can do it now. So I'm going to write it here with me. For j is equal to 10 k is equal to a j I oops is equal to j minus 1 y I greater than 0 and a I and k. This is not a program, this is a pseudocode. I plus 1 is ai. I is I minus 1, a I plus 1, a and y and 4. So let me align them. You will come to, you will become familiar with these alignments. It is not important for pseudocode, but it's always nice to have that. In programming, when you have startup follow, you put a tab there, so that you know, you can see and see, okay, that's where the for loop starts and that's where it ends. And the while loop, again, it starts here and it ends here. So it is always nice to follow that in pseudocode, so you don't have to. So what are we doing here? So let's try to understand this, this pseudocode. So we are doing a for loop. So we are counting j goes from 2 to 10. Now we are storing the jth value of, so let me write the current contents, present contents of A. I will keep on changing, because we are going to keep on changing the contents of A. But let me write the present one. We have 7 pouches. Numbers are 5, 6, 5, 9, 7, 8, 3, 4. 6, 5, 9, 7, 8, 3, 4. So we are going to temporarily store AJ. So AJ when A2 is 5. So I'm going to put note down that K is equal to 5 now. Now I'm J, I is equal to J minus 1. So that means I is 1 now. Other questions? I see a raise hand. Okay. Okay. So I is equal to 1. So just follow me. And so while, while has, this is not a program, while means, while I greater than Z, just be logical here. That's all. Y greater, I greater than Z, and so both of these conditions, while both of these conditions are satisfied, we are going to execute what is in this. We are going green. So while I is greater than 0 and AI is greater than K, which is 5, we are going to, okay, you are lost, don't worry, I will try to repeat it. And I say that, this is, you need to kind of, okay, don't worry, I will repeat this. That's all what we are going to do today. Yes, Sydney.
Can you just elaborate on what those symbols are? In the bracket under the while, where you just highlighted those 2 conditions, A square bracket, I plus 1 square bracket equals A, what?
Right. So
what does that equal? What's in that bracket?
AI. Oh, you don't see it?
Okay.
Oh,
So that's an I. Oh, okay.
Sorry. Okay, let me write it clearly. AI.
Thank you.
So what I'm doing is taking AI and putting it at the I plus 1th location. So AI means right now, since I is equal to 1, AI is A1. So I will take A1 and put it in A2. For example, I will take this and move it here. So if I take that, A1 is 6. If I take 6 and move it put it at the location of 5, we will replace it. So that means the 5 is lost. But if you look at this, but we already saved it. We saved it in a temporary variable called K. So we are saving it. So we cannot use any of these numbers. So that's the challenge here, Okay, somebody's already crying. Okay, that's fine. All you had to do is, I started with a very simple algorithm, and then I'm, sorting is probably when you got a little bit slightly advanced program, you do sort. The video is already there. It will be recorded, so you can just review it. Make sure you understand what's going on. It is not a very complex algorithm. So anyway, so let me. So how, before even going there, so let me explain how we will sort. So we will just step by step, we will bring the smallest value to the left side, because you can only move at once. You will just go here. You will just compare these two. You will just compare these two. If the high one is smaller, so in this case it is, you will just switch them. You will just make it. You will just make it 5 and 6, and just move it. You will just move on that way, and you will keep on switching them if you see, because we want it in from lowest to highest. I don't know what you mean. But, see, you're asking a question. That is why sometimes I don't put numbers, but I understand it. It would be nice to put line numbers. That is why line numbers are useful. Line 2, line 3, line 4, line 5, line 6, line 7, line 8, line 9. So this pseudocode has 7 lines. For example, if you have an equation with one of the lines, you can ask me, okay, what about this line? It is a good practice, even for pseudocode, especially for programs. You'll always have line numbers. We can refer to this line. Okay, what is the problem in this line? Things like that. So this pseudocode, we already are writing this in a very structured manner. So it has 9 lines. So store the value, and then I greater than C, and there's one more question here. So we are saying while I is greater than 0 and AI greater than K, we will just swap them. So what is happening here is, you take AI and put it in the next equation, bring it there. And then, so this is, you will just transfer them, swap. So this is a swap operation. So after this, it will be like this. After the swap operation, it's going to be like this. Nothing after that is going to change. 5, 6, 9, 7, 8, 3, 9. So after the first step, when you execute this, this is what will happen. So let's go back one more time. So I'm going back to the algorithm. For j is equal to 1 to 10, we add j is equal to 2. So j is equal to 2 to 10. We add j is equal to 2 now. K is equal to aj. So aj means a2 is 5. So k is 5. I'm saying I is equal to j minus 1. So I is 1. The while loop is run when I is greater than 0, and ai, which is I is 1. So ai means 6. ai is 6. K is 5. So 6 is greater than 5, because we want it in the ascending order, but these two are in the descending order. So we want to swap them. That's what we are doing. So ai plus 1 ai. So you take ai plus 1. I is 1. So ai plus 1 is a is 5. The second location, a2, and put it in a1. And what you have in the temporary location, you put it in ai plus 1. So here it happens this way. ai is replaced to ai plus 1. So ai plus 1, the I plus 1 location is replaced with ai. And then I is decreased, I minus 1. So I used to be 1, now it is I 0. So after executing these ones, I is 0 now. I is 0. So I am at the end of while loop. So if I had to execute these 3 lines in the while loop, line 5, 6, and 7 all the time while this condition is satisfied. Now that I execute this one, what is our situation now? Do we satisfy both of these conditions? Is I greater than 0? No. I is 0. So that means the conditions are no longer satisfied. So we get out of the while loop and we come to this point. We come to line number 9. So right now we exited the I loop, so while loop, because one of the conditions did not satisfy. So you have to check both conditions. Yes, the while loop is iterative, yes. So now we will go to, so we did all of these for j is equal to 2 to 10. Oh yeah, you're right, sorry. That was a problem. J is equal to 2 to the length of the array, so that would be 7. Yeah, that's a good point. It's a mistake in my algorithm. It should be 2 to 7 because the length of the array is 7. So we finished one of the j's. So we had to repeat this program for j is equal to 2, 3, 4, 5, 6, and 7. So I just now, so in this iteration, so we had to do the for loop. We had to do j is equal to 2. We had to do it for j is equal to 3, j is equal to 4, j is equal to 5, and j is equal to 6 and 7. 2, 3, 4, 5. So 6 times it had to run. We only finished one. So at the end of j is equal to 2, this is what we have. This is at the end of j is equal to 2. So now we are going to restart. Go to j is equal to 3. So now, we went by step. We went to the while loop. Once the conditions were not satisfied, we exited the while loop and we came to line number 9. So it is, can we end the for loop? We can end for loop only when j is equal to 7. We cannot end it now, so we have to go back and execute it for j is equal to 3. So I'm going to write the things now. So as of now, what we have in the A is this. So this is what we have in A now. At the end of the first j, this is what we accomplished. We swapped the first 2 elements. Okay, so now j is equal to 3 now. J is equal to 3. K is equal to A j. So A3, K is equal to A1, 2, 3. A3 is, if you look at, this is the present day. A keeps changing. As the program executes, A will change. So at the end of j is equal to 2, we have 5, 6, 9, 7, 8, 3, 4. So A3 is, K is equal to A3, which is 9. So K is 9. Now I have said I is equal to j minus 1. So j is 3, so I is 2. I is 2. Now we are entering the while loop. So is I greater than 0? Yes, it is 2 greater than 0. Now is AI, so AI, so that means A2, that is 6. A2 is 6. Is that greater than K is 9? K is AI is 6, K is 9. Is AI, that means A2, you can look at the present state of the array, A2 is 6. K we already stored in the variable 9.